Hello, everyone. Welcome. Hope you're doing well today. We've got some really good news today from Pfizer about the vaccine. It's very, very exciting. This is kind of what the world has been waiting for. So if all goes well, they'll start vaccinating people by the end of the year, and this might be all over by next summer. So that's great news. Yeah, no kidding. Really, really good news. I have some questions about the final. I tentatively scheduled it for Monday, December 7th. I think it'll open at 2 p.m. I haven't decided yet on the time, but I'll give you a window like I usually do. Maybe I'll start a little earlier in the day, but it'll be a good 6 to 8 hour window where you can take the final on that day. Okay. Let's see, before I get started today we just have to finish up chapter 9, and then we're going to do a quick review for the exam. All right. Can everybody hear me okay? All right. Great. Any questions before I get started?
When is the exam again? Because I'm confused. Is this Wednesday or next Wednesday?
Our next exam is a week from today. Is that what you were asking about? Exam 3 is on Monday, November 16th. Okay. Let's see, I think I froze.
Yeah, that's why he's doing it today.
Sorry, I think I froze. Let me. Can you guys hear me okay now? Am I back?
Yeah.
Okay.
Yeah, we can hear you.
Okay. Yeah, the next exam will be a week from today on Monday. That'll be exam number 3. We'll talk about that today. Okay. Anything else? All right. Let's get started here. So if you remember at the end of last time, we were in chapter 9. We were looking at periodic properties. All right. And we learned about electron configurations and how to write them from the periodic table. And we learned the connection between electron configurations, which is basically structure, and properties, right? The main theme of this class. So now we'd like to look at a few periodic properties and how they vary across a periodic table. All right, so the first one is atomic size, the size of atoms. All right, so here's the atomic radii of atoms plotted as a function of atomic number. And again, you see this sort of periodic pattern, right, that Mendeleev described for other properties, right? But we see it too for the radius of atoms, or the atomic size of atoms. And you can see that it peaks with each alkaline metal, right? And it reaches a minimum with each noble gas, all right? So let's try to, and here's another graph that kind of shows the entire periodic table. And you can see that as you go to the right, across a period, atomic radius decreases. So atomic radius decreases to right across a period and increases down a column. Right? Increases down a column. So you can see it get bigger and bigger. So let's try to understand these trends real quick. Why does atomic radius get bigger as you go down a column in the periodic table? What do you think?
The atoms are bigger, the nucleus, there's more protons and neutrons.
It's not the nucleus, because remember, the nucleus is tiny, right? The nucleus is tiny, right? The nucleus is very negligible compared to the size of the atom. So what determines the size of the atom?
Is it how many electrons?
Right, it's the electron cloud, right? It's the electron cloud. So if you think about going down a period in the periodic table, going down a column in the periodic table, look what happens. The valence electrons are an increasing principal quantum levels. Right? So the valence electrons in hydrogen is 1s1, lithium is 2s1, sodium is 3s1, and so on. And what do you know about the size of an s orbital as the n number gets bigger, as the principal quantum level gets bigger?
It gets bigger.
Exactly right. So the orbitals get bigger, so the atom gets bigger, right? Same thing for any of these columns, okay? Right now, we're going to limit our discussion to main group elements. We'll come back and see the transition elements in a minute, which are a little bit different, okay? But main group elements, as you go down a column, atoms get bigger, all right? Now, as you go to the right across a row, though, atoms get smaller, right? So why is that? Well, we got to remember something we learned already, and that is shielding and effective nuclear charge, right? So let's think about lithium for a minute, like we did before. Remember, lithium is atomic number 3, so it has 3 protons, has 3 electrons. The first 2 electrons are in a 1s orbital, and the third electron is in a 2s orbital, okay? And so these core electrons effectively shield the outer electron from nuclear charge, all right? Now, what happens when we move from lithium to beryllium? We add another unit of nuclear charge, right? So that becomes 4 plus. But we add an electron to the n equal 2 orbit, to the n equal 2 principal quantum number, sorry, right? So we're not adding core electrons, but we are adding nuclear charge. So the key to understanding this is that core electrons effectively shield valence electrons from nuclear charge, but valence electrons do not effectively shield each other from nuclear charge. All right? So if the effective nuclear charge felt by this electron in lithium is 1 plus, sorry, what do you think it is in beryllium? In beryllium, you'd have 4 plus in the nucleus, 2 core electrons, and 2 valence electrons.
2.
2 plus, exactly right. It would be 2 plus. And then when we get to boron, same thing happens. Now we have 5 protons in the nucleus, so we have 5 plus. We have 2 core electrons, and now we have 3 outer electrons, right? So what's the effective nuclear charge felt by the outer electrons in boron?
3 plus?
3 plus, yeah. So this Z effective increases. Z effective, which is effective nuclear charge, increases from left to right in the periodic table, right? So since the effective nuclear charge increases, those outer electrons feel a stronger pull, so what happens to them?
It shrinks. The atom shrinks.
Exactly. They get smaller and smaller, okay? So that explains why, as you go across a period, the atoms get smaller. As you go down the column, they get bigger because the outer quantum number, the outer principal level is bigger and bigger, so the orbitals are bigger. As you go to the right, the effective increases, so the atoms get smaller, okay? So let's do an example. Which one's bigger, nitrogen or fluorine? Nitrogen, right? Because things get smaller as you go to the right. How about carbon or germanium?
Uranium.
Germanium's bigger.
Germanium is bigger.
Right, germanium because it's lower down. Nitrogen or aluminum?
And aluminum is bigger.
Aluminum is bigger because you get bigger as you go down and bigger as you go to the left. Aluminum or germanium?
Germanium is bigger.
In this case, you can't really tell by the periodic trends because as you go to the right, things get smaller, and as you go down, things get bigger. So if you're comparing 2 elements like this, it's much more difficult to tell just based on periodic trends alone. Okay? All right, here's a question for you on the polls. Go ahead and answer this one. All right, about 10 more seconds. All right. Awesome, awesome, awesome. Virtually everybody got that. Nice, nice work. Thank you. You can see, right, as you go down from sulfur, things get bigger, and as you go to the left, things get bigger. So tin is bigger than sulfur. Okay? Nice work. All right. What about the transition elements? Well, look at the size of the transition elements. Initially, they get a little smaller, but then they get bigger again. All right? So we're going to call this trend basically flat. And why is that? Because look what happens across a transition element. The new electrons that are being added are not being added to a higher principal quantum number orbital, but to a lower principal quantum number orbital, right? So as you go to the right here, the effective nuclear charge really isn't changing as much because you're adding a unit of positive charge and you're adding an n equal, in this case, an n equal 3 electron. But it's the 4s electrons that are the biggest ones, and those are the ones that determine size. And the effective nuclear charge felt by those electrons really isn't changing as you go across a period here, okay? So those trends that we mentioned here are good for the main group elements. For transition elements, it's much less predictable, much more flat as you go across here. All right, a little bit about ions, right? How do you write an electron configuration for an ion? Well, you have to take into account the charge of the ion, right? So if you were to write electron configuration, let's say for fluorine, right? For fluorine, let's see, do I have a periodic table handy here? Yeah, for fluorine, right? You go back and you say, aha, helium core, right? And then you go 2s2, and then 2p5, right? Now, how would you write electron configuration for the F minus ion? Well, you have one more electron, right? So where's it going to go?
In the 2p orbital?
Into the 2p orbital, right? So it's going to be a helium core, 2s2, 2p6, right? Easy enough? If we're going the other way, if we're going to a positive ion, let's say we're looking at, let's say, sodium. Sodium here would be neon core, 3s1, and then you form the ion. You'd write neon core, 3s0, right? Because you lose an electron in sodium to form the positive ion, okay? Megan, do you have a question?
Yeah, it was back when we were talking about how the flat trend, the trend toward transition elements.
Yep.
Does that also have anything to do with when we, with the configuration with the 4 and 9 rows? Does that have anything to do with
No.
radius?
No, not really. No, it's just because as you go across here, you're filling the 3d orbital, where in fact it's the 4. So in other words, for the transition element, it's kind of like, instead of putting more electrons out here and increasing the nuclear charge, you're increasing the nuclear charge and putting more electrons in here. So the effective nuclear charge doesn't really change that much. Does that make sense? Okay. Very good. Now, transition metals form ions in a slightly different way. So for main group elements like fluorine and sodium, when they form ions, you just remove or add electrons in the reverse order, right? So if you're going to add electrons, you just add them in the order you would normally add them for a negative ion. For a positive ion, if you remove them, you just remove them in the reverse order of which you added them, right? So that's pretty straightforward. For transition metals, that's not the case. So for example, vanadium, let me go back to this periodic table right here. Vanadium has the electron configuration of a, if we go back, right, we see it has an argon core. And then from there, we go 4s2. And then we go 3d3, right? Now the question is, what's the electron configuration for vanadium 2+? Well, you might expect it to be an argon core, 4s2, 3d1, but that is not the case. All right, that's not what happens. In the transition elements, because the 4s and the 3d levels are so close to each other in energy, when you ionize the transition metals, they lose the s electrons before the d. All right, so the correct electron configuration for V2 plus is argon core, 4s0, 3d3. Notice I took the electrons out of the s orbital, not the d, right? And that's true for all the transition metal ions. All right, so whenever you form a transition metal ion, you take the electrons from the s orbitals and not the d. Let me define a couple words here. They are paramagnetic and diamagnetic. The magnetic properties of elements depend on unpaired electrons. All right, so remember we said that, that electrons spin, right? They have a spin, ms plus 1/2, ms minus 1/2. And that means the electron's spinning. Whenever you take a charged particle and move it around, like for example, when you make an electromagnet by winding a wire around a nail, all right, those electrons that go around that nail, they create a magnetic field and that nail becomes magnetic, all right? Similarly, when an electron spins on its axis, it creates a little magnetic field, all right? If all of the electrons in a particular atom are all paired like this, the magnetic fields all cancel each other out. Why? Because you have as many pointing up as you have pointing down, and they end up canceling each other out, right? Because if it spins one way, it forms with north up, south down. If it spins the other way, it's the opposite. So when you oppose two spins, those magnetic fields cancel out. So a paramagnetic substance means that it has unpaired electrons. And it also means it'll interact with a magnetic field. Okay? A diamagnetic substance has no unpaired electrons. All right, and it doesn't interact very strongly with a magnetic field. So here we have the electron configuration for silver. Remember, silver was one of those exceptions to the way you normally fill, right? We might expect silver to be 5s2, 4d9, but in fact, that's not what silver is. It is 5s1, 4d10, all right? Because it has an unpaired electron, it is paramagnetic, yeah? Zinc is right here, right? So it has argon core, 4s2, 3d10, yeah? So all of its electrons are paired and it's diamagnetic. What happens when you form the ion for zinc 2 plus? It's a transition metal, right? So where do the electrons come out of for the zinc 2 plus ion? Do they come out of the 4s or the 3d orbitals?
The s orbital.
4s orbital, exactly right. So they come out of the 4s. Zinc 2 plus is 4s0, 3d10, and it's also diamagnetic. Notice that if the electrons had come out of the d orbitals instead of the s orbital, what would be the magnetic property of zinc?
It would be paramagnetic.
Yeah, it would be, right? Because if you take the electrons out of here, you take one out of there and one out of there, right? You'd have 4s2, 3d8, which would mean you'd have two unpaired electrons that would be diamagnetic. So this is one way we know, right, that the electrons for the ion actually come out of the 4s instead of the 3d, because when we examine zinc 2 plus, it's not magnetic, right? It's diamagnetic. Does that make sense? All right, let's write the electron configuration and determine whether the Fe atom and the Fe3 plus ion are paramagnetic or diamagnetic. So we want Fe and Fe3 plus. So we'll go to our periodic table. Fe is right here, right? So what do? We do an argon core, and then we go 4s2, And then we do 3D, 1, 2, 3, 4, 5, 6. 3D6, right? And then if we want to draw an orbital diagram, now the difference between electron configuration and orbital diagram, remember the orbital diagram is a box with arrows in it, right? So when we draw the orbital diagram for the valence electrons in Fe, right, we'd have 4s, 3d, and then we'd have 1, 2, 3, 4, 5, 6, 7, 8. Paramagnetic or diamagnetic?
Diamagnetic. Right?
So remember the definitions. Where'd it go? Whoa! Did I lose my paper?
They're all filled, right?
Oh, right here. Sorry.
Wait.
Paramagnetic or diamagnetic? So Fe.
Oh,
So paramagnetic means it has unpaired electrons. Diamagnetic has no unpaired electrons. Does this have unpaired electrons?
yes, it does.
Yes, it does, right? So because of that, it is paramagnetic. Does that make sense?
Yes.
All right, Fe3 plus. Now remember, when we form that electron configuration for Fe3 plus, what's it going to be?
Or S0,
4s0.
and then
3D5.
3D5.
Exactly right.
Okay.
3d5. Yeah, exactly right. You take them out of the s before the d. So you got 4s0, and now you have 3d5. So 1, 2, 3, 4, 5. Paramagnetic or diamagnetic?
Paramagnetic.
Paramagnetic. Very good. Does that make sense, everyone? Okay, very good. All right, here's a quick question for you. Try this one yourselves. Okay, be careful on this one. Remember, when you form the ion of titanium, it's 2 plus, where are the 2 electrons going to come out of? The s or the d orbitals?
Yes.
The s orbitals, right? They come out of the s orbitals. That's true for all transition metals. When you form the ions, take the electrons out of the s orbitals before the d orbitals. Before you take them out of the d orbitals. Okay, 5 more seconds. Okay, not bad. The answer was A. That was, and most of you got that, but some of you didn't. And I think it's just because you probably took the electrons out of the wrong orbital. So when I form the Ti2 plus ions, remember, because it's a transition metal, these are the electrons that go out. So this is 4s0 3d2. So when you draw the orbital diagram, right, this is the 4s orbital, these are the 3d orbitals, right? You're gonna have 2 electrons in the 3d orbitals, right? And notice, because of that, they're unpaired. Unpaired means it's paramagnetic, all right? Don't forget. Okay, very good. What about the size of ions? Well, you can see here, these are the size of atoms and their ions. And what you see is that when you form a positive ion, the positive ion is much smaller than its neutral atom. So cations are much smaller than the corresponding neutral atom, okay? Why is that? Because typically you're taking out the valence electrons. The valence electrons are in the biggest orbitals, right? You take those away and all you're left with is the core. Now those core electrons are being, the net positive charge of the atom holds those core electrons in even tighter, right? The diagrams are 1 box for S. Yes, that's correct. For orbital diagrams, 1 box for S, 5 boxes for D, because each box represents an orbital. All right, what about anions? Anions are adding extra electrons, all right? So anions are much bigger than their corresponding atoms, because you're adding electrons, but you're not adding any protons, right? So that creates extra electron-electron repulsions, which then make the anion much bigger than its neutral atom. So anions are much larger than the corresponding neutral atom. All right, the next thing we want to look at is something called first ionization energy. The ionization energy of an atom is the energy it takes to remove an electron from the atom. So ionization energy, energy required to remove an electron, right? So for example, we can write an equation like this. Na gas goes to Na plus gas plus 1 electron, and the ionization energy, and we put a 1 there to indicate the first ionization energy, is equal to plus 496 kilojoules per mole. What does it tell you that it's plus? Is this process endothermic or exothermic?
Endothermic.
Endothermic, right? It takes energy to remove the electron, right? Why? Because the electron is being attracted to the nucleus. Kind of like a weight is attracted to the earth, right? To pull a weight away from the earth, you got to put energy in. That's endothermic. To pull an electron from a nucleus, you got to put energy in. That's endothermic. All right? Similarly, the second ionization energy, we can write an equation like this. And notice the second ionization energy is 10 times bigger than the first. Removing that second electron is 10 times harder than removing the first electron. Why do you think that is?
Because it's closer to the nucleus.
Exactly right. When you remove the first electron from sodium, you're removing that valence electron, which is further away from the nucleus. When you remove the second electron, you got to remove a core electron, right? Which is closer to the nucleus, and now that atom has a positive charge, okay? Ionization energy is the energy required to remove an electron. Energy required to remove an electron, okay? Sorry, I abbreviated it. My bad. Okay, let's see. So, what are the trends in ionization energy? Well, let's see what happens as you move down a column. As you move down a column, ionization energy decreases. Why do you think that is?
More valence electrons to take away, or it's, they're further away from their.
Yes.
Sorry.
Yes.
I'm mushing my words.
Yes. As the atom gets bigger, the electron is further away, and therefore it's a lot easier to remove. Okay. Therefore, it's a lot easier to remove. All of this is will also be available posted after the class, right? So if you missed something during class, don't worry about it. You can always go back and go to the video and fast forward to the things you missed, okay? Okay, so what about as you go to the right? What do you notice happens?
Takes a lot more energy.
It increases, right? Increases as you go right across a period. Why is the ionization increasing as you go to the right? What else is happening as you go to the right?
Atomic radius decreases.
Pardon me?
The atomic radius.
Yes, the atomic radius decreases, and that happens because effective nuclear charge increases, right? So if effective nuclear charge increases as you go to the right, it makes sense that it's harder to pull the electron away. Yeah? Because you got to pull it away from a bigger and bigger net charge as you go to the right. Okay, so here we go. Let's choose the atom in each pair that has the higher first ionization energy, aluminum or sulfur. Froze. Sorry, can you hear me?
Sure.
Froze there for a minute. What do you think? Which has the higher ionization energy, aluminum or sulfur?
Sulfur.
Sulfur, correct. Arsenic or antimony?
As AS.
AS, yep, AS, very good. Nitrogen or silicon?
It's going nitrogen.
Nitrogen, yes, because it goes, ionization energy decreases and then decreases some more. And then, of course, if you go this way, you can't tell, right? You can't tell as you go this way because
So it would be fair to say that since the radius to the right, when moving to the right decreases and moving down increases, is the opposite to ionization.
Yes, correct. Yep, exactly right. Yep.
And when it's like that in corner meeting like bromine and Xe, that means that we can predict.
Correct. Can't predict based on periodic properties. Very good. Okay, let's have you try one here. Five more seconds. Okay, very, very good. virtually all of you got that. It's nitrogen, right? Because as you go down, ionization energy gets smaller, right? And then as you go to the left, let's see, where's germanium? This way it gets smaller again, right? So nitrogen is bigger than germanium in terms of ionization energy. Okay, very good. Glad to see that. Sounds like you guys are understanding. Let's look at successive ionization energies now. And when you look at successive ionization energies, the important thing to realize is there's a huge jump from valence electrons to core electrons, right? There's a huge jump when you're ionizing valence electrons compared to core electrons, right? So here's sodium, right? Remember where sodium is. Sodium's right here. It has one valence electron. The first ionization energy is 496, and then it jumps to 4560, right? 4,560. Why? This is a valence electron. This is a core electron, right? Now let's look at magnesium. How many valence electrons does magnesium have?
2.
2, right? 2. So notice we see the first ionization energy, 738. The second one, about double the first. Boom! Huge jump at the third one, right? The valence electrons are easier to remove than the core electrons. So you're going to always see a jump in going from valence electrons to core electrons. Okay? So let me have you try this. Now think about what we just learned. You expect to see a jump where? Between the last valence electron and the first core electron. Right? You expect to see a big jump in ionization energy between the last valence electron and the first core electron. So here are the ionization energies that are given, right? And it's asking you which of these third period elements does this data belong to? Okay, it looks like maybe some of you are struggling a little bit with this one. Oh no, here it comes. You guys are getting it. Where does the big jump happen? From here to here? No. Where does it happen? Between what? Right here. Between 5 and 6. Right? The big jump happens between 5 and 6. So, what is the last valence electron? Is it this one or is it this one? Is it the fifth one or the sixth one?
This one.
The fifth one, right? So this is telling you that this element has 5 valence electrons, right? Because 1, 2, 3, nice steady increase, and then bam, big jump, right? That's because you've gone from valence electrons to the core electrons. So basically you got to figure out, okay, which third period element has 5 valence electrons? The right answer is D, phosphorus, okay? D, it has 5 valence electrons, so those 5 come off easily, and then the 6th one, boom, big jump. All right, again, most of you got that, so nice work. Thanks for following along. Thanks for participating in the polls. All right, 2 last periodic properties, and then we'll be done. Electron affinity is the energy associated with gaining an electron. So it's kind of the opposite of ionization energy, okay? Kind of the opposite of ionization energy. First of all, electron affinities tend to be negative. So for example, chlorine plus 1 electron goes to Cl minus. Electron affinity is negative 349 kilojoules per mole. So this is what? Exothermic or endothermic?
Exothermic?
Exothermic, right. It gives off heat. Why? Because the electron is attracted to the nucleus, even though there's other electrons there that also repel the electron, okay? It's still negative, all right? It's still exothermic. But the trend for electron affinity is not so clear as it was for ionization energy. Notice the trends here. First of all, notice that most of them are negative, just like we expect, all right? But if you look at a trend down a column, there's not really much of a trend. And even across a row, the trend is not very smooth. But what we can say is that generally speaking, electron affinity increases as we go to the right. Generally increases to the right. And we're going to say no change going down. No change going down a column. Okay? That's the trend for electron affinity. Lastly, metallic character. So if you remember, we've talked about metals and nonmetals before already in this class. Metals have a tendency to do what in their chemical reactions?
Lose electrons?
Lose electrons, right? Lose electrons. So from the trend in ionization energy, which is the energy required to lose an electron, we should be able to tell the trend in in metallic character, right? So as you go down a column, atoms get bigger, right? And it's easier to remove an electron, right? So therefore, as you go down a column, things become more metallic, right? However, as you move to the right across a period, the atoms get smaller because Z effective increases. The ionization energy gets bigger, which means it's harder to lose an electron, which means that metallic character decreases. Okay? So metallic character increases as you go down, right? Decreases as you go right. All right, and so therefore that's why, you know, all the nonmetals are over here in the upper right, right? And all the metals are over here in the lower left. Okay? You can see a really nice transition by looking at, for example, going down the 5A family. So you got nitrogen, which is a nonmetal, phosphorus, which is kind of a metalloid, arsenic, which is a metal, and then Sp and antimony and bismuth, right, which are metals, right? So you go from non-metal to metal as you go down. And then you see the same thing as you go to the right on the third period, right? Very metallic elements. You get to phosphorus kind of in between, and then very non-metallic elements. All right. All right, so this table in your book summarizes all these different properties, right? And these are the trends that I want you to know for the exam, okay? All of these trends here in radii, first ionization energy, electron affinity, and metallic character. All right, any questions on those? Is that clear?
You want us to be able to apply these or
Of course.
just the definitions?
No, you got to be able to apply them too.
Okay, I just want to make sure.
Yeah, no, good question. Abe, do you have a question?
Yeah.
Yeah.
What is successive ionization energies? Like, what does that mean?
That means, when you have like a series of them one after the other. So like IE1, IE2, IE3, right? These are successive ionization energies, right? So for phosphorus, right? This is how much it takes to take away the first electron, second electron, third electron, fourth electron, fifth electron, then bam, you hit a big wall. Why? Because now you're taking away the core electrons. So ionization energy jumps way up.
Okay.
Yeah? Cool. Okay, very good. I'm going to stick around afterwards as usual for further questions, but I do want to get to our review. And we're running a little short on time, so let me just jump to that right now. And then if you have questions on the review or on anything else, you can, of course, just stay after class and I'll answer those questions, okay? So the exam next Monday will cover chapters 7, 8, and 9. All right. It is very similar to the other exams, right? Multiple choice format, and you'll take it on Canvas, right? Over the same hours, between 2 and 10 p.m. Okay. Let's look at what was in chapter 7, right? 3 chapters ago. We talked about the nature of energy and thermodynamics. So a lot of definitions there. Right, definition of energy, definition of heat, definition of work, definition of potential energy. Make sure you know all those definitions, okay? Know what heat and work are, right? Know that, this will come up in a minute, but I'm just gonna write it down here so remember. Delta E, the change in internal energy, is equal to the sum of the heat and the work, right? So if a system, right, if you have a system, it exchanges energy with its surroundings, and it can do it via heat or via work, right? And delta E for the system is just the sum of those two. And remember, energy going out, whether by heat or by work, carries what kind of a sign? Negative. Energy coming into the system carries what kind of a sign?
Positive.
Positive, okay? Whether it be heat or work. All right, then we talked about calorimetry. So know both types of calorimetry that we talked about, a bomb calorimeter and a coffee cup calorimeter. Remember that a bomb calorimeter measures delta E, the change in internal energy. A coffee cup calorimeter measures delta H, the change in enthalpy, all right? These two quantities are similar and they're related, but they're not exactly the same thing, all right? Delta E is the sum of all the heat and work. Delta H is just the heat at constant pressure, all right? And then, of course, we calculated delta H reaction. You should know what delta H reaction means and how to quantify it, and then how to calculate it using Hess's law, right? So from some related reactions, if you have a couple related reactions, you can oftentimes manipulate them to get delta H for an unknown reaction, right, using Hess's law. And then the second way is from enthalpies, tabulated enthalpies of formation, right? The sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. And you would normally look those up in a table, right? But of course, on the exam, they'll just be given on the exam. All right, so you can find them. The periodic table and table of constants that you lose for the last exam will also be able to be used on this exam. All right, I'll resend you that. And again, like the last exam, you'll be able to use a one-page cheat sheet, right, where you can write down whatever you want. Okay. All right, Chapter 7, skills. So remember, this list of skills you can find in the back of your book. It tells you what exercises and what examples in the book will show you how to show you that skill, right? But this is a good checklist to go through, right, as you prepare for the exam, right? So know the different types of energy and be able to convert between energy units. Know about changes in internal energy in terms of heat and work. In other words, using this equation, delta E equals Q plus W. Determine heat from temperature changes, right? Q is equal to MC delta T. Be able to use that equation. Calculate quantities in thermal energy transfer. So if you have two substances transferring energy one from another, you might be able to calculate the final temperature, say, for example, of the two substances after the energy transfer is complete. All right? Be able to analyze processes involving pressure volume work, right? So the equation work is equal to minus P delta V. All the equations will be shown right after this, okay? Can you guys see that? Maybe I should just play this as a slideshow. It might be easier to see. Is that better? Where were we? Yeah. Analyze energy changes for combustion reactions inside a bomb calorimeter. So for a bomb calorimeter, right, be able to calculate delta E. Predict endothermic and exothermic processes. And what I mean by that is just know the difference, right? Know the difference between them. Perform stoichiometric calculations involving the enthalpy of reaction. What I mean by that is if you have some process, you know, A goes to B, and you know delta H is equal to some number, let's say minus 10 kilojoules, right? And you're given a certain amount of A, let's say grams of A, you're given 10 grams of A, 10 grams of A, find heat evolved, right, when 10 grams of A react. So what you do is you go from grams of A to moles of A, right, to kilojoules, right? And if there's a 2 here, you got to take that into account when you go from moles of A to kilojoules, right? So it's basically stoichiometry all over again, but with energy as well, okay? Analyze enthalpy changes for reaction coffee cup calorimeter, right? So be able to know how to find delta H from data using a coffee cup calorimeter. Analyze how changes in chemical reactions affect the enthalpy of reaction. And what I mean by that is to be able to calculate if you double the reaction, what happens to delta H?
Double it.
You double it. If you flip the reaction so that it's backwards, what happens to delta H?
Sign's flipped.
What do you do? One more time.
Flip the sign.
Flip the sign, right? You flip the sign. And if you add two reactions together that sum to a third reaction, and you know delta H for the two reactions, then delta H for the third reaction is just what?
Some of the other ones.
That's exactly right. Very, very good. Thank you. All right. And then lastly, be able to determine the standard enthalpy change for a reaction using standard enthalpies of formation. Okay? Those are those tabulated things. Oops. Where are my equations? Oh. Okay. Hang on for a second. Let me let me get those equations. I think I left them out accidentally. 1 second. Apologies. Do-do-do-do-do.
I thought you were looking for the chapter 7 equations.
Thank you. You're right.
Sorry, I just wanted to make sure. I didn't know.
No, you're totally right. Thank you. Almost there, guys, sorry. All right. All right, so chapter 7, equations, equation for kinetic energy, right? The equation for the change in internal energy of a chemical system, always final minus initial, right? Because that is, internal energy is a function of state, right? It just depends on the state of the system. So you can always just do final minus initial, all right? Energy flow between system and surroundings, any energy lost by the system is gained by the surroundings or vice versa, so that the two are equal to each other in magnitude, but opposite in sign. So relationship between internal energy and Q and W, so delta E is equal to Q plus W, right? Relationship between heat, temperature, and heat capacity, right? So Q is equal to C times delta T. This C is total heat capacity, right? But many times we'll have specific heat capacity, which gives us the heat capacity per gram of something, in which case you have to multiply by the mass, right, to get the total heat capacity. Work is equal to force times distance. You won't have to do any calculations for that, but you will need to know the definition of work. The equation for pressure volume work, right? Work is equal to minus P external delta V. That's like when a cylinder expands or contracts. Change in internal energy of a system at constant volume. Delta E is equal to QV, right? Because if the volume is constant, then delta V is 0, so there's no work. So delta E is just equal to QV. That's what happens in a bomb calorimeter. The heat of a bomb calorimeter, Q calorimeter, is equal to C calorimeter times delta T. Remember, the C calorimeter will usually be given, or you'll be given some data by which you can calculate it, okay? And from this, you can get delta E for the reaction. Heat exchange between a calorimeter and a reaction. Q calorimeter is equal to minus Q reaction, right? Q system is equal to minus Q surroundings, right? It's the same idea. Relationship between enthalpy, internal energy, P, and volume. This you don't really have to worry about too much, or really not at all, but you do need to know that delta H is equal to the heat exchange at constant pressure, right? That's the definition of delta H. All right, and then lastly, how to find delta H reaction, right, from heats of formation, right? So delta H for a reaction is equal to the sum of the heats of formation of the products times their stoichiometric coefficients minus the sum of the heats of formation of the reactants times their stoichiometric coefficients. And remember that the heats of formation of pure elements is what?
0.
0, right? It's 0. Very good. All right. Chapter 8, we talked about the nature of light. So know what light is. It's both its description as a wave phenomenon and as a particle phenomenon. We talked about atomic spectroscopy, right? The line spectrum being given off by elements when you excite them, typically with electrical current. We talked about the wave nature of matter, right? The double slit experiment, the de Broglie wavelength of electrons, right? And then we talked about the quantum mechanical model of the atom, right? So the quantum numbers and the orbitals and all of that, okay? Key skills here, be able to understand the wave properties and wave behaviors of light, right? Know the different things like amplitude, wavelength, things like that. Be familiar with the electromagnetic spectrum, right? Know relative wavelengths and in the visible region and also in the entire electromagnetic spectrum, right? So you should know, for example, that UV light has a shorter wavelength than infrared light, all right? Or that red light has a longer wavelength than blue light, for example, okay? Know the particle properties and particle behaviors associated with light, right? So know about photons and how to calculate their energy. Know about the wave properties of matter and be able to calculate things like the wavelength of an electron at a given velocity. Be able to describe orbitals using quantum numbers. Know what quantum numbers are allowed, what combinations are allowed and which combinations are not allowed. And then calculate the energy change of an electron transition in an atom according to the Bohr model, but also according to the quantum mechanical model, and be able to calculate the wavelength of light associated with those transitions. Okay? So equations and relationships, what's new? C over lambda, right? The nerd joke. Hey Joe, what's new? C over lambda. Relationship between frequency and wavelength, right? C is the speed of light. Relationship between energy and the energy of a photon, right? E is equal to h nu if you describe it in terms of frequency. E is equal to hc over lambda if you describe it with respect to wavelength. The de Broglie relation, right? The wavelength, lambda, of a particle of mass m moving at velocity v, right? The de Broglie wavelength, the wave nature of matter, okay? Heisenberg's uncertainty principle. The uncertainty in the position times the mass and the uncertainty in the velocity is greater than or equal to h over 4 pi. You won't have to do any calculations using this equation. I just want you to understand it conceptually, right? You can never simultaneously have zero uncertainty in the position and zero uncertainty in the velocity, right? Because that product has always got to be greater than or equal to this number, all right? And remember that the position is associated with the particle nature of light, the velocity is associated with its wave nature, and so therefore those are complementary properties, right? Complementary properties. The energy of an electron in an orbital of quantum number n, right, for the hydrogen atom, it's given by that equation, and you can calculate the change in energy that occurs using this equation, right? And remember that you can do that for an atom and then figure out the wavelength of the photon emitted by whatever that change in energy being, whatever that change in energy is, you set it equal to the energy here and you solve for lambda, right? So for example, kind of problem is an electron hydrogen atom makes the transition from n equal 1 to n equal 5. What wavelength is associated with that transition, right? So you figure out the energy difference between those two energy levels and you'd set that equal to E is equal to hc over lambda. All right, chapter 9. We talked about periodic properties and the periodic law. So know what those are. We talked about sublevel splitting. This is where in the hydrogen atom, remember the s, p, d orbitals, they all have the same energy for a given principal quantum number. But that's not true in multi-electron atoms. Why? Because of this sublevel splitting, right? And that's due to shielding and penetration. So make sure you understand those terms. Be able to write electron configurations from the periodic table, know what effective nuclear charge is, and be able to predict periodic trends in atomic size, which we talked about today. Know about the different ion properties, be able to predict whether ions or neutral atoms are going to be paramagnetic or diamagnetic. And then trends in electron affinity and metallic character. All right, chapter 9, skills. Be able to write electron configurations for elements, right? I won't be asking you to write anything for the F block, right? And but I do want you to know how to write electron configurations for the D block, all right? And those 4 exceptions that I mentioned in class, okay? Draw orbital diagrams for elements. What's the difference? An electron configuration is like 1s2, 2s2, 2p6, right? An orbital diagram is a box with electrons in them, okay, with the electron arrows in them. And you should be able to do that, both of those based on the position in the periodic table. Know the periodic trends in atomic size. be able to predict magnetic properties based on whether or not something has paired or unpaired electrons, predict the relative size of ions from periodic trends, predict relative ionization energies for atoms and ions based on periodic trends, so kind of the stuff we were talking about today, and then lastly, metallic character based on periodic trends. Chapter 9 equations, none. No equations for this chapter. Okay, that's what's going to be on the exam. The exam is next Monday, so you have a lot of time. You have a problem set to finish between now and then. You have a practice test to finish between now and then. All right. And I'm happy to take any questions. Abe.
Yeah, can you go over sublevel splitting and then the orbital diagram for chromium?
Yeah, sublevel splitting is when you have, for example, for hydrogen, right? If you plot energy and you plot the orbitals here, right? You got 1s, 2s, 2p, 3s, 3p, 3d. Right? That's for the hydrogen atom. Right? But when you get to multi-electron atoms, that's no longer true. So for all atoms other than hydrogen, right? You have 1s, 2s, 2p, 3s, 3p, and so on. So the sublevel splitting means that in the hydrogen atom, all of these have the same energy. In multi-electron atoms, they don't. Right? So the sublevels split in terms of their energy. Does that make sense?
Wait, say that one more time, please.
So in the hydrogen atom, the s and the p orbitals in a given principal level have the same energy, but in the multi-electron atom, they don't. Those sublevels split. The s sublevel and the p sublevel have different energies.
Okay, I get it now.
Okay, and that's due to the penetration and shielding effects that we talked about in class. What was the other question again?
Can you show the orbital diagram for chromium?
Yeah. So for chromium, which is right here, right? You might expect it to be an argon core, right? And then 4s2, 3d, 1, 2, 3, 4, right? That's what we might expect, but that's not what it is, right? Because there's this special stability associated with a half-filled shell in the d orbitals, right? So instead you have chromium, argon, core, 4s1, 3d5, like that. Does that make sense?
Yeah, but I wanted like the diagram.
Oh, the diagram, yeah. Okay, so then you have 4s1, 3d. So there's 5 boxes here. Each one has 1 electron.
Got it. Thank you.
Yeah. Diana.
Is gold included in that? Because I know what is it, chromium.
The only ones that I'm going to ask you about, or potentially ask you about, would be chromium, molybdenum, copper, or silver. There's other exceptions in this block, but I won't ask you about those. These are the only 4 you have to know.
Okay, and then when we're writing the configuration for periods 6 and 7, when we're adding the F, why is it that it's 4 and?
Right, so remember, for the d orbitals, the quantum number for the d orbital that's filling in a particular period is the period number -1. For the lanthanides and actinides, it's the period number, which is 8 and 9 minus 2. Sorry, which is 6 and 7. 6 and 7. So this would be the 5F, and this would be the, sorry, these would be the 4F, and these would be the 5F.
Okay. And with those, we would, when we're taking away electrons, we'd have to take away from.
I'm not gonna ask you any F or any of these down here, just because there's so many exceptions to those. But when you have ions of transition metals, yes, the S electrons are removed before the D.
Okay.
All right, other questions? Okay, I think I'll officially end class here, and I'll stick around in case you have some other questions. But thanks, everyone.